Have you ever stopped to wonder why some things just happen? You know, why ice melts or why coffee gets cold. We usually just blame it on one word: entropy. But here's the thing. That common idea of entropy as just messiness or disorder, it's not just incomplete, sometimes it's flat out wrong. And to see why, let's start with something you probably have in your kitchen right now.
Okay, so here we have a bottle of Italian salad dressing. It's just been sitting there, right? It's at a constant temperature, not getting hotter or colder. In the language of physics, it's reached thermal equilibrium. And what's really interesting is that this state, this equilibrium, is also the state of maximum entropy. But hang on a second. If maximum entropy means maximum disorder, why does this look so neat? The oil and the vinegar are in these nice, clean layers. A shaken-up, completely mixed dressing would look way more disordered, wouldn't it? Well, this little contradiction is what we're going to call the salad dressing paradox. And it's the key to understanding what's really going on. So let's dive in. Section 1. The salad dressing paradox.
See, everything that happens in the universe is basically the result of a cosmic tug-of-war between two fundamental forces. On one side, you have enthalpy. Think of it as nature's desire for stability, for everything to get to its lowest, most relaxed energy state, kind of like a ball rolling to the bottom of a hill. And on the other side, you have entropy, which is the drive for energy to spread out, to disperse. So when these two are pulling in opposite directions, who wins?
That brings us to Section 2, energy versus disorder.
Turns out there's a referee in this cosmic battle. As Chemistry LibreText puts it, there's a single master variable that decides if a change can happen all by itself, what scientists call a spontaneous process.
And that master variable, it has a name, Gibbs free energy, or delta G. It's the ultimate decider. It brilliantly takes both of those drives, the push for lower energy from enthalpy and the pull for more dispersal from entropy, and combines them into one single value that tells us, yes, this will happen, or no, it won't.
And this is it. This is the formula that runs the show. The change in Gibbs free energy equals the change in enthalpy minus temperature times the change in entropy. Did you catch that letter right in the middle? T for temperature. Temperature is the crucial referee in this whole game. By multiplying that entropy term, temperature gets to decide which side gets a boost and ultimately wins the tug-of-war.
All right, let's break down how this works. Section 3. The Great Decider. This chart lays it all out beautifully. Look at that top row. If a process releases energy and increases disorder, like burning something, enthalpy and entropy are on the same team. It's a win-win. It's going to happen, no matter the temperature. But look at those middle two rows. That's where things get interesting. One force wants to go, the other wants to stay. And that's where temperature becomes the tiebreaker, making things like water freezing happen only when it's cold and water boiling happen only when it's hot. In that last row, if something costs energy and creates order, well, that's just never going to happen on its own.
Let's really see this in action. Section 4. How temperature changes everything.
Let's use boiling water, something we've all seen. At 90 degrees Celsius, the Gibbs free energy is positive. The energy cost of breaking those water bonds is just too high for the entropy gain at that temperature. It won't boil. Then, right at 100 degrees, the boiling point, delta G hits 0. The two forces are in a perfect stalemate. That's equilibrium. But crank the heat just a little more to 110 degrees and delta G goes negative. Now, that temperature-boosted entropy term is huge. It overwhelms the energy cost, and the water boils all by itself.
And this brings us right back to our salad dressing. So why does it separate? Well, mixing the oil and vinegar would increase their local disorder, sure. But by separating, the oil molecules and the water-based vinegar molecules get to form much more stable, lower energy bonds with themselves. It's a huge drop in enthalpy. And at room temperature, that drive for lower energy is so powerful that it wins the tug-of-war. The energy that gets released by separating actually heats up the surroundings, which increases the total entropy of the whole universe way more than mixing ever could. So that neat, orderly-looking bottle, it's actually the state of higher universal entropy. Paradox solved.
Okay, so let's get to our last section, Section 5. Entropy isn't just chaos. If entropy isn't just about being messy, then what in the world is it really? Let's do a little test to challenge our intuition.
Take a look at these two patterns. They were both made by randomly placing squares on a grid. But one of them had an extra rule, an extra restriction, which means it has lower entropy, fewer possible ways it could have been made.
So, which one do you think is the one with higher entropy? The one that was less restricted, more truly random? Go with your gut. I'm willing to bet most people are pointing to the one on the right. It just looks more random, doesn't it? Smoother, more evenly spread out.
Surprise! It's actually the pattern on the left. The one on the right, the smooth one, was made with a rule no two squares could touch. That restriction is what makes it look so orderly. True, unrestricted randomness, it's clumpy, it has clusters, and it has big empty voids. Think about the stars in the sky. They aren't perfectly spaced out, are they? We see galaxies and giant empty spaces precisely because that's what real randomness looks like.
The physicist Dan Steyer nailed it with this quote. He said, "The average configuration will be uniform, but each individual configuration will, typically, be clumpy." That's the key. The average of all possible random outcomes is smooth, but any one typical outcome you actually see is going to be lumpy and irregular.
Now, don't get me wrong. This doesn't mean the messy room idea is totally useless. It's such a powerful and relatable metaphor that it's become a punchline, like in this great New Yorker cartoon. It's a handy shortcut, for sure, but as we've seen today, it just doesn't tell the whole amazing story. So what is the big story? What's the main takeaway? Well, we have to go all the way back to the 1850s, to Rudolf Clausius, the scientist who first came up with the word entropy. He stated this incredibly profound law of nature. The entropy of the universe tends to a maximum. That's the second law of thermodynamics. Every single spontaneous thing that happens, from salad dressing separating to stars being born, it all increases the total entropy of the universe.
And because the universe's total entropy can only ever increase, it gives time its direction. It's why time only flows one way. You can't unscramble an egg. You can't unburn a piece of wood. Those processes are irreversible, because going backward would mean decreasing the total entropy of the universe, and that would violate one of the most fundamental rules of reality. Entropy is literally the arrow of time.
And that leaves us with one last, truly massive thought. We started with a bottle of salad dressing, and we've ended up at the fate of the entire cosmos. So if entropy is this relentless arrow of time pushing everything forward, where ultimately is our universe pointing? What does that final state of maximum entropy even look like? Now that is something to think about.